Hello. So in this part of the video, we will solve chapter 16 in class exercise 1 problems. There are 4 problems in class exercise 1, and for these problems, we need to use these equations. First equation, all these equations are for pure rotation of the rigid body, where theta is the position variable, omega is the angular velocity, alpha is the angular acceleration. So we know from the linear velocity equation that angular velocity is rate of change of position with respect to time. Remember that theta is in radians. Angular acceleration is rate of change of angular velocity with respect to time. And the third equation, which relates angular acceleration with change of position equal to angular velocity and change in angular velocity. This equation is derived from first two equations by eliminating dt. For a rigid body in pure rotation, the velocity at any point on the rigid body can be calculated by multiplying the angular velocity of the rigid body with the distance of the point from the center of rotation. This is the scalar approach. The vector solution can be obtained using cross product where V is equal to omega cross R. For rigid body under pure rotation, all the points they have two components of the acceleration. Tangential component, which is the product of alpha multiplied by R, and normal component of the acceleration, which is omega square multiplied by R. Now, if the acceleration is constant, we can use one of the three ready-made equations to calculate either the final velocity or the final position. But remember that these equations can be used only when acceleration, angular acceleration alpha is constant. Once again, I revise the units. Theta is in radians, omega is in radians per second, and alpha is in radian per second square. So with this information, we are good to go with the in-class exercise problem number 1. So for this problem, the angular velocity of the disk is defined by omega equal to 5t square plus 2 radians per second, where t is in seconds. Determine the magnitude of the velocity and acceleration of point A on the disk when time t is 0.5 seconds. Point A is here on the disk and it is 0.8 meters from the center of rotation. Disk rotates counterclockwise, so if we consider that the disk is in xy plane, then the z-axis is passing through the center of the disk and perpendicular to the plane of paper. Now, from the equations, we know that the velocity of point A can be calculated by multiplying angular velocity with the distance vector from the center of rotation to point A. So we know that the angular velocity is function of time. So this is 5t square plus 2 multiplied by r. Now the value of r for this problem is 0.8 meters and we need to calculate the velocity at 0.5 seconds. So if you substitute these values for t equal to 0.5 seconds and r is equal to 0.8 in this equation, we can calculate the velocity of point A, which is 2.60, and the unit for this velocity is meters per second. Do not confuse between omega and v. Omega is angular velocity, it's in radians per second, and v is linear velocity, that's in meters per second. This is our first answer. Now to calculate the acceleration of point A, we need to calculate both the normal and tangential component of the acceleration. So the normal tangential component of the acceleration can be calculated using the equations, that is alpha angular acceleration multiplied by radius. Now angular acceleration is not given, but angular velocity is given as function of time. So angular acceleration can be calculated by taking the derivative of the given angular velocity. So then this will be d by dt 5t square plus 2 multiplied by r. So this will be 10t multiplied by r. In this equation, when we substitute t is equal to 0.5 seconds and r is equal to 0.8 meters, we get the tangential component of the acceleration, which is 4 meter per second square. This is 80. For normal component of the acceleration, an, which is omega square multiplied by r. Again, we know the equation for omega, which is 5t square plus 2, and the square of this entire equation, because it is omega square multiplied by r. In this equation, when you substitute t is equal to 0.5 and r is equal to 0.8, and when you solve the equation, you get normal acceleration 8.45 meters per second square. So the total acceleration of point A in this example is combination of tangential and normal acceleration, and A is square root of tangential component square plus normal component square, and this number is 4 square plus 8.45 square and square root of that, which is 9.348 meters per second square. And this is the total acceleration of point A, acceleration of A. Okay. That's our final answer. If you see this graphically, the position of velocity, then for A, this is the position vector from the center of rotation. So velocity of A is perpendicular to this position vector and points in the direction of rotation. So this is the velocity of A. Tangential component of the acceleration for A is in the same direction because angular acceleration is positive. That means the speed of the disk increases with respect to time. And normal component of the acceleration is always towards the center, so this is the normal component of the acceleration for point A. And total acceleration, which is that we have calculated, is that lies somewhere in between. This is the total acceleration of point A, which is the combination of tangential acceleration and normal acceleration. That's the end of problem. Next three problems are related to motion transmission using gears and pulley. So let's quickly revise this portion, which has already been covered in the theory in the previous video. So consider that this is gear A, which rotates counterclockwise, then gear B rotates clockwise. Let's say this is the point P, which is the point of contact between gear A and gear B. In order to properly transmit the motion from A to B, at the point of contact, both the gears, they must have the same surface speed V, and they must have the same tangential component of the acceleration. We know the equation for surface velocity, which is omega r. That means if this is, let's say, Ra, which is the radius of gear A, and this is Rb, which is the radius of gear B. Let's say omega A is the angular velocity of gear A, and omega B is the angular velocity of gear B. Also, let's say alpha A is angular acceleration of gear A, and alpha B is angular acceleration of gear B. Now I have drawn alpha in the same direction as omega A, so I am assuming that the speed of the gear increases with respect to time, so acceleration is positive. For some reason, if the speed of the gear decreases with respect to time, then omega still stays in counterclockwise direction, but alpha changes the direction if the disk or gear slows down. Anyways, in this example, they both are in the same direction. So now, and when this parameter is constant, that is velocity and tangential acceleration, we can derive the equation from velocity that omega A multiplied by Ra for gear A is same as omega B multiplied by Rb for second gear. That means if we know the dimensions of both the gears and we know the angular velocity of one gear, then we can actually calculate the angular velocity of the second gear using this equation. And when tangential acceleration is constant, we can derive the second equation, which relates alpha r for both the gears. So alpha a for gear A multiplied by the radius of gear A, which is same as alpha b, that is angular acceleration of gear B, multiplied by the radius of gear B. Again, that means if we know the radii of both the gears and angular acceleration of one gear, we can calculate the angular acceleration of the second gear. So for next three problems, we will make use of these two equations. Okay. Keep in mind that omega r for both the gears is same because the velocity is constant, and alpha r for both the gears is same because tangential component of the acceleration is constant. Okay, let's discuss this problem. If gear A rotates with an angular velocity of omega A is theta A plus 1 radians per second, where theta A is the angular displacement of gear A measured in radians, determine the angular acceleration of gear D when theta A is 3 radians starting from rest. Gears A, B, C, and D have radii of 15, 50, 25, and 75 respectively. So this is the example of a gearbox. This gearbox has 4 gears. Gear A is the input gear, and gear D is the output gear. Well, this is actually shaft D, but yeah, you can actually extend it to gear D. That is the output gear. This type of gearbox is called compound gearbox, which is used for speed reduction. So gear A is mounted on a shaft which is driven by, let's say, an engine or electric motor. Gear B is in mesh with gear A, so B is driven by A. Now gear B and gear C are mounted on the same shaft. That means they both have same angular velocity and same angular acceleration. And gear D is driven by gear C, so it will have the different angular velocity and angular acceleration. What we need to do in this example is we have been given the angular velocity of gear A as a function of angular position. So that is what we know for gear A, and we need to calculate the angular acceleration of gear D by using the calculation. So the first step is if we calculate angular acceleration of gear A from this angular velocity, then we can easily calculate angular acceleration of gear B using the uh, equation that relates alpha r for gear A and gear B. Once we calculate the angular acceleration of gear B, what do you think about the angular acceleration of gear C? It will be the same as angular acceleration of gear B because they both are mounted on the same shaft. And then once we have the angular acceleration of gear C, we can calculate angular acceleration of gear D, again using alpha R equation. So the problem is very simple once we figure out how to calculate the angular acceleration of gear A. So let's begin. And also be careful that all these values for radii are in millimeter. In our equation, we convert them into meters. So you need to divide each number by 1000. Okay. So let me write this value. So radius of gear A is 0.015 meters. Radius of gear B is 0.050 meters. Radius of gear C is 0.025 meters. And radius of gear D is 0.075 meters. Okay. Let me draw a simplified diagram for this gearbox. So this is gear A, which is small gear. This is the shaft of gear A, which is connected with gear B, which is a big gear. And this is the shaft of gear B. From here to here, this distance is radius of gear A. From here to here, this distance is radius of gear B. So this is A, this is B. Now C is mounted on the same shaft as that of B. So B and C, they both have the same angular speed and same angular acceleration. And this distance is radius of gear C. And finally, we have our output gear, which is gear D, and that has a separate shaft. So make sure, see, pay careful attention here. I have connected B and C on the same shaft, but A and D are not on the same shaft. Okay. And this distance from here to here is radius of gear D. So at this point of contact, both A and B have the same velocity and tangential component of the acceleration. At this point, both C and D have the same velocity and tangential component of the acceleration. So now the question is, how do we calculate angular acceleration from the angular velocity? It's not straightforward here because angular velocity is not function of time, it is function of theta. That means we need to make use of this equation. Alpha d theta is equal to omega d omega. And we need to apply this equation for gear A. So this will be alpha A d theta A is equal to omega A d omega A. From this equation, we can rearrange these terms. We can take the d theta onto the right side. So now it's omega A d omega A divided by d theta A. So what we need to do here to calculate the angular acceleration of gear A is we need to multiply. Now I'm substituting the value of omega A, which is theta A plus 1. It's given in the problem. Multiply that with the derivative of this term with respect to theta. And that will be 1 plus 0. So actually it's 1 only. So now angular acceleration of A is theta A plus 1. That's alpha A. Value of theta A is given in problem, which is 3 radians. So now you substitute 3 radians here. So you'll get the angular acceleration of A, which is 3 plus 1, so 4 radian per second square. That's the first part of the problem. For the next part, we need to calculate. So now the problem is simple. Now next step is we need to calculate the angular acceleration of B. So A and B, so A drives gear B and they have common point of contact, so they both have the same angular acceleration, tangential component of the acceleration. So we can say that alpha A multiplied by Ra is equal to alpha B multiplied by Rb. From this equation, we know the radius of gear A, we know the radius of gear B. We have already calculated angular acceleration of gear A, so we can determine the angular acceleration of gear B. So alpha B is 4, which is alpha A multiplied by 0.015 divided by radius of gear B, which is 0.05. And this number is sorry, this number is 1.2 radians per second square, alpha v. And again, from how do we get this equation? Once again, because both A and B have the same tangential component of the acceleration. Okay. Now we continue applying this. So now this is the angular acceleration of B. Now can you guess what is the angular acceleration of C? That is same as angular acceleration of B because they both are mounted on the same shaft. So this is also 1.2 radians per second square. And the last part is we need to calculate angular acceleration of gear D in this problem in here. So between C and D, they have a common point, and that common point must have the same tangential acceleration. So for gear C, whatever is the tangential component of the acceleration, it's same for gear D as well. So we need to substitute the equation alpha r for tangential component of the acceleration. So alpha C RC is alpha D RD. And from this, we can calculate angular acceleration of gear D, which is alpha C, which is 1.2, multiplied by RC, which is 0.025, divided by RD, which is 0.075. And when you do this math, you will get alpha D, which is 0.4 radians per second square, and that's our final answer. Next problem. The gear A on the drive shaft of the outboard motor has a radius of 0.5 inches, and the mast pinion gear B on the propeller shaft has a radius of 1.2 inches. Determine the angular velocity of the propeller in 1.5 seconds. If the drive shaft rotates with an angular acceleration of 400 t cube radians per second square, the propeller is originally at rest and the motor frame does not move. So this line is useful, that the propeller is originally at rest. That means initial angular velocity is zero, or the angular acceleration. Now this is the motor shaft. This is gear A, which is bevel gear, which drives another gear B, and the propeller shaft is mounted. A propeller is attached with the same shaft on which gear B is mounted. So if we calculate the angular velocity of gear B, then the angular velocity of the propeller is same as that angular velocity because they both are on the same shaft and there is no gear in between them. Now for this problem, first we need to calculate the angular velocity of bevel gear A. Now for gear A, we have been given the angular acceleration as a function of time, which is 400 t cube radians per second square. So from that, we need to calculate angular velocity. And you know that angular velocity is integration of angular acceleration. So you're familiar with this equation, alpha is equal to d omega by dt. So we know now, we have been given alpha, we need to calculate omega. So we need to write the equation for omega. So d omega is equal to alpha multiplied by dt. Now we need to integrate this equation on both sides to find the exact value of omega. Initial angular velocity of gear A is 0, again because it's originally at rest. Final angular velocity, that's what we are calculating. Initial angular acceleration is 0 when time t is 0, and the time goes from 0 to 1.5 seconds. Read this line in the problem, 1.5 seconds. Okay. So now we substitute the equation of alpha in this integral and we integrate it on both sides. So this will become now omega A, because we are calculating for gear A, equal to, this is 400 t cube dt. So integral of that is 400 t raised to 4 divided by 4, and we need to substitute the values of t from 0 to 1.5. So when we solve this integral, we get omega A as 506.24 radians per second. This is the angular velocity of gear A after substituting t is equal to 1.5 seconds. And next step is we need to calculate angular velocity of gear B. Now A and B, they are in contact. So at the point of contact, they both have the same surface speed. So we can say that velocity of gear B is same as velocity of gear A, because they have the same, because they are in mesh. Now we can substitute the velocity in terms of omega B RB is equal to omega A RA. And in this equation, uh, we know the value of omega A, which is we have calculated. We know the radius of gear A that's given in the problem, which is 0.5 inches, and radius of gear B, which is 1.2 inches. So we can calculate omega B. So omega B is equal to 506.24 multiplied by 0.5 inches divided by 1.2, and this number is 210.93, and I'll convert this to three significant figures. So this is 211 radians per second square, and that's the angular velocity of gear B. And the angular velocity of the propeller is same as this angular velocity because they both are on the same shaft. That's the end of problem. And the last problem from chapter 16 in class exercise 1. The driving belt is twisted so that pulley B rotates in the opposite direction to that of drive wheel A. If A has constant angular acceleration, alpha A equal to 30 radians per second square, determine the tangential and normal component of acceleration of point A located at the rim of pulley B when time t is 3 seconds, starting from rest. So instead of gears, now we have belt and pulley in this example. This is driving pulley and this is driven pulley. So let me write it for you. So this is driving and this is driven. Now, what we know for this problem is that the wheel A has constant angular acceleration. This is very useful information because now if the angular acceleration is constant, you know that we can use one of the three equations here. Okay, so let's go back to our discussion. What we need to do in this problem is we need to determine the tangential and normal component of the acceleration for the point B, which is located at the rim of pulley B. So if I just draw this diagram for pulley B separately here, then this is the center of rotation for pulley B. And this is the point, any point, it doesn't matter which point you select, but this is any point that we select here. Let's say this point is at distance 125 millimeters. I'll just convert this into meters. So this is 0.125 meters from the center of rotation for pulley B. At this point, we need to calculate what is the tangential component of the acceleration for that point and what is the normal component of the acceleration. So we are calculating normal and tangential component of the acceleration for this point with respect to the center of rotation for pulley B. In order to find these two accelerations, we need to know what is the angular velocity of pulley B and what is the angular acceleration of pulley B. So we need to calculate omega b and alpha b. Once we have omega and alpha, we know how to calculate tangential and normal component of the acceleration because we have this equation here. So once we have alpha and omega for pulley B, we can just multiply alpha and omega with the distance from the center. In this example, that point is at the rim of the pulley. So this R for is nothing but the radius of the pulley, and that will give us the tangential component of the acceleration. And we multiply the square of angular velocity with the radius of pulley B, and that will give us the normal component of the acceleration for pulley B. Okay, so let's begin. So first step is, how do we calculate the angular velocity of pulley A? Because first step is we calculate angular velocity of pulley A, and then using that information we calculate omega B and alpha B. So now because the acceleration is constant, we can apply this equation that final acceleration angular velocity of pulley A is equal to omega A 0, which is the initial angular velocity of pulley A, plus angular acceleration multiplied by time. Now both the pulleys start from rest, so initial angular velocity is 0. Angular acceleration is given in the problem, which is 30. You can look at this number, 30 radians per second square, and multiply this with the time, 3 seconds, it's given here, and then you will get 90 radians per second square for omega A. This is the angular velocity of pulley A. Now there is no slip of built between pulley A and pulley B. It doesn't say that anywhere in the problem, but yeah, you assume that there is no slippage of built. Okay, so you can consider literally that A and B are similar to gears. Okay, so now A and B, they both have the same surface speed, so velocity of A is same as velocity of B. That means omega A RA is equal to omega B RB. So from this equation, we can calculate omega B, which is omega A. We have just calculated 90 multiplied by radius of pulley A, which is 0.2 meters, divided by radius of pulley B, which is 0.125 meters, and then this number is 144 radians per second. The next step is we need to calculate angular acceleration. So both for A and B, they both have same tangential component of the acceleration. Okay, so alpha A RA is same as alpha B RB, and from this equation you can calculate alpha B. So alpha A is given, which is 30, RA is 0.2 divided by 0.125, so alpha B is 48 radians per second square. And finally, once we have both these numbers, we can calculate tangential component of the acceleration for the point on pulley B. So this tangential component of the acceleration will be alpha B multiplied by R, where R is the distance of that point from the center of rotation. Okay. So alpha B is 48 multiplied by 0.125, and this number is 6. And what is the unit? It's meters per second square. Okay, so it's not radians because this is acceleration and not angular acceleration. And finally, normal component of the acceleration, so this is ABT, this is ABN, which is omega B square multiplied by R, and omega B we have just calculated here, which is 144 multiply square, multiply by 0.125, and we get this number as, it's a big number, it's 2592 meters per second square. Okay, and these two are our final answers. Normal component, tangential component of the acceleration, and normal component of the acceleration for the point which is at the rim of pulley B.